We present Bayesian optimization for sample-efficient policy improvement and robotic manipulation. Learning complex robotic manipulation from pure robotic exploration is prohibitively expensive, and even more so in sparse reward reinforcement learning settings. Thus, imitation learning has emerged as a prevalent technique for initializing robotic manipulation policies. While imitation learning does improve robotic performance, it also relies on a dataset of human demonstrations, which are costly to collect. In addition, the initial policy typically requires improvement, which means running it on a robot and collecting feedback from the environment. Especially with a real robotic system, this implies an additional massive time commitment. Thus, the challenge of imitation learning is to initialize from as few demonstrations and improve with as few additional exploration steps as possible. In this work, we present a framing of a sparse RL problem as black box optimization. We introduce a low-dimensional GMM update to aid policy improvement. We demonstrate the effectiveness of our approach in simulated and real-world robotic tasks. We start with a base policy modeled as a GMM fitted to an initial set of human demonstrations. This policy is updated using a delta to form the full policy used by our robot. We let the policy run for j episodes and average the sparse returns that we receive from the environment. We encapsulate this process as a function, which serves as the objective maximized by the optimizer. The return obtained by an update is collected in a dataset and used by the optimizer to model a distribution of possible returns. Using expected improvement, the optimizer draws a new update and lets the evaluation function determine its value. Our GMMs model the association of a state to its derivative. They consist of an activation weight per component, the component's means, and the covariances of each component. We update these GMM parameters using different schemes. The weights are updated with a simple addition and renormalization. The means are updated solely additively. The challenge with the covariances is that they grow quadratically with the size of the state. This is problematic for Bayesian optimization as it works best with a small number of parameters. We keep the growth in check by first only updating the state derivative variance, as it is the only parameter set used for inference. We then propose updating the remaining parameters either by scaling their eigen decomposition or by performing a simple Euler rotation. Both methods are linear with respect to the size of the state space. We evaluate our approach in 3 scenarios in both simulation and real world, in which the robot has to open a hatch, a drawer, and a door. The agent is rewarded only with a sparse success or failure signal. We compare our approach against 2 baselines. The first is online GMM, a naive baseline in which we simply refit the base GMM model to additionally gathered successful trajectories. The second is our previous approach SAC-GMM. It also proposes GMM updates, but does so at regular intervals during the execution based on environmental observations using a SAC agent. All approaches start from the same GMM policy. We run all approaches for a maximum of 500 episodes, and track the final model's success and the number of episodes needed to achieve 80% success. We fit the initial GMM policy to 10 teleoperated demonstrations for the tasks. In our simulated experiments, we find that BOP-GMM achieves 80% success 40% earlier than SAC-GMM. SAC-GMM, on the other hand, achieves higher overall performance. We also find that both methods work best with our newly proposed GMM covariance updates. The combination of updating both means and covariances performs worse than just our update. Our online GMM baseline is not able to compete with these results. In our real-world experiments, we apply our approach to similar setups as in our simulations and compare once more to SAC-GMM. We find again that BOP-GMM is faster than SAC-GMM. Here we give a brief impression of the difference between the initial GMM policy and the one yielded by optimization. We conclude that we were successful in applying black box optimization for efficient GMM-based policy improvement. We demonstrated our low-dimensional updates to be very successful both for BOP-GMM and SAC-GMM. Going forward, we see potential for combining both BOP-GMM and SAC-GMM for optimizing a policy together. Further, we think more informed stopping criteria for BOP could be derived to stop the exploration early. For a more detailed understanding of our approach and a more thorough discussion of our results and the insights we draw from them, we refer you to our full manuscript.
We present our novel method BEV-CoR, addressing camera radar fusion for BEV map and object segmentation. We obtain descriptive vision features from a DynoV2 backbone and utilize a learnable radar encoding. We then lift the image features to the BEV space and propose a novel query initialization scheme that exploits radar features. Finally, we fuse both modalities in an intention-based manner and perform multi-class BEV vehicle and map segmentation. Since passive sensors, such as RGB cameras, suffer from challenging illumination conditions, we separate the new scenes validation split into day, rain, and night scenes. Here, we present qualitative results for our BEV-CoR and the derived camera-only variant. We report the metrics averaged over the entire scene. Our studies clearly indicate the benefit of utilizing automotive radar in addition to surround view vision. For further quantitative results, including more baseline comparisons, please consult our paper. Thank you for your attention.
In this video, we present our work, Panoptic Auto-Distribution Segmentation. Deep learning has led to remarkable strides in scene understanding, with panoptic segmentation emerging as a key holistic scene interpretation task. However, the performance of panoptic segmentation is severely impacted in the presence of out-of-distribution objects, that is, categories of objects that deviate from the training distribution. To directly address these challenges at the task level, we introduce panoptic out-of-distribution segmentation that focuses on holistic scene understanding while effectively segmenting OD objects. Our proposed task aims to predict both the semantic segmentation of stuff classes and instance segmentation of thing classes as well as an OOD class. To facilitate research in this new task, we present a suitable evaluation metric, benchmark dataset, baselines, and a novel approach, POCs. We introduce the Panoptic Auto-Distribution Quality Metric, which jointly assesses in-distribution and out-of-distribution performance using the geometric mean of the panoptic quality for each distribution. We extended standard autonomous driving datasets with OOD instance segmentation annotations to establish two challenging benchmarks Cityscapes OOD, and BDD 100K OOD. Our proposed approach PODS builds on top of a base panoptic segmentation network by incorporating modules specially designed to embed out-of-distribution capabilities based on prior knowledge of in-distribution classes. In the figure, boxes with lock on it correspond to the base panoptic segmentation architecture, whose weights are fixed when training our incorporated modules. We incorporate an OOD contextual module that complements the robust in-distribution semantic features of the shared backbone with both global discriminatory and fine local OOD object representations. Subsequently, we introduce an additional task-specific decoder equipped with dynamic modules alongside the existing ones. This allows for adaptive integration of OOD features while preserving the strong prior in-distribution features. The unique dual task-specific decoder configuration benefits further from our novel alignment mismatch loss. This loss encourages learning by balancing consensus and divergence between the two heads. This enables learning finer details within in-distribution semantic classes and what lies outside. Furthermore, we incorporate a data augmentation strategy to facilitate the training of our novel model. For benchmarking, we constructed 6 baselines. Among them, our proposed approach, PODS, achieves the highest PODQ score. We qualitatively demonstrate the significance of our task by comparing a panoptic segmentation network with our PODS architecture in real-world driving scenarios. A comparison utilizes in-house data from Freiburg with OOD objects. We believe our task shows great potential for robotics community and will aid in robust scene understanding. Thank you for your attention.